We've seen how to find equivalent resistance for resistors in series. That's easy. We just take the sum of all the resistors and that gives us our equivalent. So now let's see how resistors in parallel combine. Given the circuit, let's just do a simple one with two resistors in parallel connected to a voltage source. Let's call this Vs, this will be R1, this will be R2, and then let's go ahead and label our currents. So we've got a current that originates from the source, we'll call that Is, that comes to this node and will split. So some of the current will take the branch down R1, we'll label that current I1, and some of the current will take this branch that goes through R2, so we'll call that I2. Now in the last video we introduced KCL, Kirchhoff's current law. By KCL we have that the sum of the currents going into a node is equal to the sum of currents going out. So in this case we only have one current coming in, so our equation is just Is is equal to I1 plus I2. Okay, so the other thing that we know is that however much source current is generated by this source depends on the equivalent resistance that is seen by the source. So if you imagine you stand at the source and you're looking into the circuit this way, what's the equivalent resistance you see? So we'll write here that Is depends on our equivalent seen by the source. So this is our source, Vs, looking into the circuit. So if I had some open terminals here, and I just replaced this, these resistors in parallel with one equivalent resistor, Req, then that's going to give me how much source current is produced, basically by Ohm's law. So we can say by Ohm's law, which is V equals IR, we have that our V is the source voltage, we have our current is Is, and then the R here is our equivalent. Alright, so that's just applying Ohm's law to the equivalent circuit. Now remember, this equivalent circuit is actually this, right? If we were to kind of work backwards, and apply Ohm's law at each of these branches, we can get an expression for the voltage drop across both of these resistors. So that'll be my next step. If we apply Ohm's law at each branch, well, what do we get? We get that the voltage drop across R1, so I'll call that V1, is equal to the current that goes through R1, so I1 times R1 itself. Great, and then same story for V2, that's equal to I2, because that's the current that takes the branch down through R2, times R2 itself. So this is just Ohm's law applied here and applied here. Okay, great. So as you can see in this circuit though, our resistors are connected directly in parallel with the source. So we actually know, we already know V1 and V2. We know the voltage drop across this resistor. We know the voltage drop across this resistor because they're connected directly to Vs. So I'll say, because R1 is in parallel with R2 is in parallel with Vs, we know that V1 is equal to V2 is equal to Vs. Okay, great. So then these equations become so at the branches we have that V1 is equal to Vs is equal to I1 R1, so that implies that I1 is equal to Vs over R1. Similarly, since we know V2 is equal to Vs, and that's equal to I2 times R2, that implies that I2 is equal to Vs over R2. Great. Okay, so if we take these equations and we plug these into the equation we got from KCL, if we plug these into, this is the equation that we got from KCL, I1 plus I2, then we get that IS is equal to Vs over R1 plus Vs over R2. So I can write this as, if I factor out a Vs, this is 1 over R1 plus 1 over R2. Okay, great. So that's fine, but what we really want is an expression for R equivalent. So let's go back and use our Ohm's law equation for our equivalent circuit here. So that was this guy. Vs is equal to Is times Rq. So now let's revisit our Vs is equal to Is times R equivalent. Okay, great. So if we take this and if we plug this into that Vs, here's what we get. Is is equal to Vs times 1 over R1 plus 1 over R2. We make our substitution and we get this is equal to Is times R equivalent times 1 over R1 plus 1 over R2. So now on the left-hand side here I have an Is. On the right-hand side I also have an Is. So these guys are going to cancel. Cancel, cancel. And then I'm left with R equivalent is equal to 1 over R1 plus 1 over R2. Okay, so this is how we find R equivalent for resistors in parallel. And more generally, because this is a specific example with just two resistors in parallel, we can say that R equivalent for resistors in parallel can be obtained by taking 1 over R1 plus 1 over R2 plus 1 over R3 and however many resistors you happen to have in parallel. So this is for parallel resistors. Okay, great. So let's see an example. Suppose we have, let's do 3 resistors in parallel. Let's let the first one be 2 ohms, the second can be 3 ohms, the fourth can be 4 ohms. So we use the equation that we just derived to find R equivalent. So we get R equivalent is equal to 1 over R1, which is 2, plus 1 over R2, which is 3, plus 1 over R3, which is 4. I'm going to do a little bit of common denominators here. 6 over 12, 4 over 12, plus 3 over 12, so it gives us 1 over 13 over 12. So our R equivalent is 12 over 13 ohms. If I put that in my calculator, that's about equal to 0.92 ohms. So let's think about that for a second. This is a little bit less than 1 ohm, which is less than all of these resistors. So it turns out, I'll write this, because of the reciprocal relationship for R equivalent, adding more resistors in parallel actually decreases the overall resistance. So more resistors decreases R equivalent when resistors are oriented in parallel.